going to start recording. 3 sig figs. Next one. 2 sig figs. I think I heard a 3 out there, so let's check that one. The 1 and the 2 are significant digits. Okay, we then have to evaluate what rule we follow. Rule 2 means no decimal point. Rule 3 is if there is a decimal point. Do we see a decimal point? No. Okay. Yes, there's an implied decimal point. That's irrelevant. We have to see the decimal point. There's no decimal point specified, so we fall under Rule 2. So the 0 has to be controlled both to the left and the right. We look to the left, what do we have? Sig fig, so that's fine. We look to the right and we have nothing. Right? Which means the 0 does not count as a significant digit. We only have 1 and 2, which means we have 2 sig figs. Next one. 3. It jumps up with just the simple application of that decimal point. Right? Next one. 4. Next one. Next one. 2. Okay.
Why is that one 4?
Double back. I was kind of, no, I'm fine with that. I was just kind of surprised I didn't hear any responses as to why it was 4. So, 1 and 2, absolutely. Since we've been underlining them in red, let's go through and keep that. 1 and 2 absolutely are significant digits. We now have to decide on the zeros. With our rule sets, okay, if there's a decimal point, it just needs to be preceded by a significant digit. Okay, so there is going to be a method to the madness on how we decide if these zeros are significant. Because if I start with that last 0 and I look to the left, is that digit significant?
Yes.
Is it underlined? No, we haven't identified if it's significant or not. So that 0 is up for grabs. We have no idea what to do. So starting our determination if a 0 is significant by looking at the very last 0 is not the best option. So let's not look at the last one. Let's look at the second to last one. When I look to the left of it, what do I have? Significant digit. Because I have a decimal point, I'm under Rule 3, which means our 0 is now significant. Now that it's significant, I can underline it, move to the next number across. I run into another 0. I look to the left of it. What do I have? A significant digit. Because it's a significant digit, what does that make that last 0? Significant. I now have 4 significant digits. Right? So the location of the 0 relative to the decimal point is kind of irrelevant. The decimal point just tells us which rule set we have to follow. Okay? And then we're looking at our 0's location relative to significant digits. If there's no decimal point, I need a significant digit to either side. Okay? If there is a decimal point, I only need it to the left. It is left, isn't it? Yes. Okay? Make sense? The 2 to the upper right. We zero back in on those. All right, why are those both just 2? Zero's not preceded by a significant digit. Which then brings up another question. Why provide the exact same number with a 0 versus not a 0? It's not even really on our part to trick you. It's on your part to trick yourself. Okay, believe it or not. That's the only reason this is brought up. Okay, because if I asked you to provide that first number, okay, to draw out the decimal 0.12, more than likely what you will write will be 0.12. Do you guys see the decimal that I just wrote there? Barely. If you're dealing with pencil, you're probably just hitting the paper. Very small point shows up. Particularly if you've now done a problem several times over. You probably have carryover pencil lead from the last time you did the mistake, and you took a number that could have been 12 and have now made it a decimal, 0.12. Or you took a number that was supposed to be 0.12 and now it's all of a sudden become 12. So by putting a 0 in front, now you go, wait, why is there a 0 in front of 12? That doesn't make any sense. And you pause ever so short a time. You look at what your work says and you go, oh, there's a decimal point there, and then you make it darker so that you see it. Okay? That is the only reason I bring up those two numbers, is that very often decimal points disappear in our haste to go through and solve questions. Okay? So when it comes to lab work, you don't have me for labs, you don't have to work, or at least you don't have me yet. Okay? I will almost always write with an answer written as 0.12. I usually grade in purple. I'll circle it with a big old arrow, and you'll see me write leading 0. Probably with an exclamation point. And depending on how many times I've seen it, I might even write minus 20. Okay, so that you panic and go, oh my God, I lost 20 points. No, I just wrote minus 20 so you paid attention to what I wrote. Okay? So you need to remember that leading 0 because it doesn't mean anything as far as significant digits, but it does make a really important difference in finding your decimal place. Okay, so watch out for that when you move into your lab work. Questions on that? And now we had a nice little distraction. Sig Figs in the next one. And in our last one? 3. Everybody happy with Sig Figs? At least as happy as you can be. Okay. This on its own is probably the extent of what you would expect to see on the final. Okay. A lot of you have to go through and take 151 and 152. Okay. I will straight up say right now, I'm probably the only faculty at this campus that thinks Sig Figs are pretty much useless. Okay. Because when you move into the lab, your calculations give you your Sig Figs. There's very little thought that has to go in, oh, I have to calculate out my Sig Figs. So really the only time that you run into Sig Figs being an issue is in lecture. Well, if I don't lecture 151 and 152, but all the other faculty do, and they really ream you on Sig Figs, I kind of have to carry the party line and make sure you're aware of that. Right? So be careful with your Sig Figs, particularly within this first section. After exam 1, Sig Figs become much less important, and particularly on a multiple choice exam, we're not going to give you the answer choice of 1 Sig Fig in a calculation, 2 Sig Figs in a calculation, 3 Sig Figs in a calculation, and 4 Sig Figs. Because all we're asking there is a Sig Fig question. Okay, when in actuality, we really want to get to the larger points. Can you do the rest of the math or the rest of the calculations? Okay, so practice it. Try not to get too irritated with Sig Figs, okay, but do what you can. Okay. How many of you are confident with Sig Figs as it is? Okay, I was hoping for a little more than that, but okay. Okay, we'll assume the rest of you are just tired and can't lift your arm. It gets more complex. We run into this issue of measurement versus exact. Okay? A distance, a mass, a volume, time are really only as accurate as the device we're using to measure them. Are there measurements that don't require an instrument? For instance, how many, those are quarters, how many quarters are shown in this image? So you can tell me, there are 7, right? Yeah. 7 quarters. Just call it Q. How many Sig Figs? Okay. Measurement versus exact. How many quarters are there? Exactly 7, or are you measuring 7? It's exactly 7, which means how many Sig Figs are there? An infinite amount of Sig Figs. Okay? We don't want to say 0, because when we move to the next part, where we have to carry Sig Figs through a calculation, you can only carry Sig Figs according to a certain number. If you have 0 Sig Figs to start with, what's your answer going to have? 0 Sig Figs. Well, if no digit is significant, you have no answer to write. That kind of defeats the purpose of doing the calculations. So there are certain potentially conversions and observations that are exact values. Indeed, most often, those are counting systems, where we're counting specifically how many things there are. Okay? And we trust that our human brain is not tricking us and that there's actually 6.978 quarters there. Okay? Kind of makes sense? Okay. So all of you that were happy with Sig Figs that didn't raise your hand, now what are you saying about Sig Figs? Yeah, that's what I thought. Okay. So exact values right, have infinite sig figs. Another classic example, particularly when we look at conversion factors, is inches in feet. How many inches are there in a foot? We have 12 inches in 1 foot. How many sig figs in those numbers? Infinite. There are exactly 12 feet. How do we know there's exactly 12 feet and 12 inches in 1 foot? Because we've defined it to be that. Okay? So a lot of these definition things give you infinite sig figs. So you got to watch out for those as well. Typically, if you're doing a conversion, your conversion from a measurement should never make your sig figs disappear. So if your answer or your measurement has 20 sig figs, how many sig figs should be in your conversion? 20, at least. Okay, so you almost always match so that you don't lose sig figs. So why the fuss over this? Okay, well, it moves into then what do we do with these measurements once we have them? Well, we can do a variety of mathematical operations, addition, subtraction, multiplication, and division. So when we look at addition and subtraction, what happens with our sig figs? Well, our result is only going to be as precise or have as many sig figs in, let's not say sig figs. Our result is only as precise as our least precise measurement. Okay, so if we take a look at this calculation, we can add this up, and what we should get as a number, see if I can think through this, I believe, do this kind of quickly, I think it's going to be 1.15.633.62. Really good with my mathematics. Those of you up close may be laughing at me. Okay? That measurement has a lot of numbers in it. Okay? But what we've got to go through and do is deal with the proper number of sig figs. So on an exam, we may give you this and say, okay, what's the answer? One of the answer choices will be this exact number. What's the issue with this exact number? It's wrong. It doesn't have the proper number of sig figs for our calculation to be valid. Okay? So when we do addition and subtraction, our result is only as precise as the least precise measurement. So which measurement is the least precise? It's the top one. It's the one with the fewest string of significant digits coming after. So not the number of sig figs, but the number of places. Okay, that's where our precision is coming from. We are only as accurate up to, and I always get these backwards, so please bear with me, the 10th place, right? Okay, which means when we get to our answer can only be reported to the 10th place. And instead of reporting 115.63362, I have to report 115.6.
So we get it wrong if you put the big number.
And grams. You would get it wrong if you put the big number. Okay? So your calculator will spit out a lot of different numbers. You have to interpret those numbers. Calculators are getting fancier. Some of them will take into consideration sig figs, some of them won't. So watch out for that. Yeah.
Why is it 0.6 instead of 0.5?
Calculation, you just round off.
You should just add that up. So in theory, my number was 115.63362.
So you're just canceling out.
Yeah, we just get rid of the rest of it. Yeah. We'll talk about rounding in a little bit. Okay? So some people go through, well, we have all those numbers, why can't we keep them? Well, the issue comes from what number comes after that 3? What number is that right there? Our mind says it's 0. This is a measurement. We have no idea what that number is. It could be 0. It could be 9. Okay? Because the measurement doesn't give us that data. It's not there. It's not specified. It can be anything in that sequence. Which means really what we're doing is comparing these two calculations, where it's 0s all the way through versus if they're 9s where everything's left. And when we run those calculations, we do get a significant difference between those numbers. Okay? Which is why when we go to report our answer, we report to that least precise value. And we only go out to the tenths place in this case. Okay? Kind of makes sense? Okay, what makes this even trickier? Well, multiplication and division, of course, is a different calculation or a different rule set. Okay, for those of you that can't see the box very well, I'm trying to draw in the box. When we deal with multiplication and division, our rule is that we have the same number of sig figs in our answer as the fewest significant digits in our calculation. So if I want to calculate the area of, that's not a square, but a rectangle, what do? Okay, base times height. What's the base of this rectangle? 7.28 units, thank you. Times the height, which was 4.6 units. Okay. We can punch it into our calculator, and I think I give the answer up here. We end up with this answer, 33.488 units squared. So our calculator spits that number out. Okay. Now we have to decide, based on our sig figs, how much of that answer is actually valid. So based on our rule set for multiplication and division, our answer needs to be reported out to the fewest significant digits. So we go back to our calculation. How many sig figs in 7.28? 3. How many sig figs in 4.6? 2. Which means the answer needs to get reported to 2 sig figs. There's my first 2. The answer must be defined as 33 units squared. You write 33.5, 33.48, 33.4, you're wrong. Okay? Because we don't have the accuracy in our measurement to carry that digit. Which does seem odd, but that's the way science works. Okay? Yeah.
So I don't know. You take the least amount of sig figs, and then you look at the number, and you search out those 2 sig figs, and that's your answer.
That's your answer. Yep.
If it was 33.5, would you round it to
Oh,
34?
we'll deal with rounding in a second. I think that's actually the next slide.
Thank you.
Yeah. Questions? Everybody kind of okay with that? At least you've got the rule. Okay? You now have to apply the rule again and again and again to get it beat into your head, but you've got the rules. Yes. You got it? Okay. Okay. What happens when we round? So we've got some new problems here. We take 0.75 plus 0.585. We get the number 1.335. How many sig figs, or where, how do I want to say this? What answer should we report for our addition and subtraction? Okay. We would go to our hundredths position, and we would have 1.3, and now we've got an interesting dilemma that some of you started to ask about. Okay. That next digit is 5. Are we closer to 3 or are we closer to 4? We're actually stuck right in the middle. This comes down to rounding. We have to come up with a rule set for rounding. Unfortunately, the rule sets for rounding, at least in my experience, are not consistent. Okay? Which again, why I don't like sig figs, because if we can't be consistent in the problems we give you, or the consistency in the textbook, or the consistency in our exams, it's very hard to insist that consistency upon you. Okay? The rule set that I will try to maintain my very best throughout the rest of this semester is here, which I think I fixed the typos on. If our first non-significant digit is less than 5, then we leave our last significant digit alone. So if we look at our addition subtraction, we went out to the hundredths place. So we would say we'd have 1.3, and now our first insignificant digit is the 5. Okay. If it's less than 5, it stays as a 3. Okay. But it's 5 or bigger, we add 1 to the last digit. So that means our number becomes 1.34 grams. That's what gets reported as our answer. All right, what happens with the multiplication? We go through and deal with our multiplication. How many sig figs do we get in our answer?
2.
Just 2. Yeah, I switched it up on you. Right? But we look at our first insignificant digit. It's a 5 or bigger. I have to add 1 to the previous digit, and our answer becomes 37. The decimal point is right there. 37 units squared. Right. The issue with rounding is that if we've got all these numbers and we start rounding early in a calculation, let's say we've got to run through 20 calculations. If we do each calculation individually and round at each of those steps, okay, we can potentially scale our number off significantly enough that we don't get the correct answer, okay, or within the correct thresholds. On a multiple choice exam, it's not that bad because if you're off by maybe 1 or 2 numbers, you're probably correct. You just made a rounding error. You can guess that. But in mastering chemistry, where they're being very particular about you hitting exactly the right sig figs with the exact right rounding, a rounding error can mess up your whole number. Okay, which means when you go through and do a calculation, you need to round at the end of the calculation, okay, which can be tedious if you have 20 steps, because you have to go through each of your 20 steps and decide how many sig figs can I carry through this step. Okay, this step gives me 2. The next step gives me 3, but that first one was 2, so I have to go back to 2 sig figs. Next step gives me 3, still 2. Next step gives me 2, okay. Next step gives me 1. Well, now my answer can only be reported to 1 sig fig. Meanwhile, your calculation, you're carrying all of the decimal places all the way through to get to the very end, so that once you know how many sig figs need to show up in your answer, you can then go back and say, okay, do I need to round? Where do I round? Okay, so you have to keep track of all of these steps all the way through. Okay? Not that bad. It's a bit tedious, but you will find that it does come pretty quickly. Again, because under most circumstances, when we run a conversion, how many sig figs do we typically carry? 3. So if everything carries 3 sig figs, you get to your answer, 3 sig figs, round to 3 sig figs, and you're pretty much done. Okay? Questions about that? Okay. What do you guys think? Some practice? Okay. So we'll take a couple minutes. If we go ahead and continue on here. First number of sig figs? 3. Why are there 3? The zeros at the end, okay, won't count because there's no decimal point. Okay, so they need to be bound by a number on either side. Okay, so the 0 in the middle we do count because we have a significant digit to either side of it. 2, how many sig figs?
6.
Well, every single one of these sig figs counts, and we end up with 6. All right, because with that decimal, as long as we have a sig fig in front of it, we can count it. 2a, how many sig figs?
3.
1, 2, 3, 4, 5, 6, 7 sig figs. Yeah, we'll get back to your number in a second. Okay. This is one that was brought up by a student, which is why I modified my rules when it came to no decimal point. Because in my rules it used to say, as long as it has a significant digit immediately to either side of it, for it to count. Okay, that's not true. As long as there's a significant digit anywhere to the left, anywhere to the right without a decimal point, your zeros will count. So that when we go through and look at this number, we look to the left, there's a 1. We look immediately to the right, but there's none, or we can't tell, so we keep going. We hit the 2. That is a significant digit, which means our 0 counts. We then do the same thing with the next 0. We look to the left. We just said that 0 is significant. Can't tell, can't tell, can't tell. Significant. And we go through and do that for all of them. So as long as there's a significant digit to either side, or to both sides, does not have to be immediately next to it. Okay? Those zeros will count as sig figs. Okay? So we got 7 sig figs in that one. Next answer, in theory, your calculator spits out 129 point, spit out 03? 04. Is that exactly what it spit out? Oh, 041. All right, what answer do we need to report?
As the slide says.
Why 29.04?
Because the answer is at the bottom of the slide.
So that's a nice way to cheat. Yeah, I found my little sneaky way of doing math really fast. Why 04?
Smallest numbers to.
We're doing addition, least precise measurement. First one goes out to the thousandths. Next one goes out to the hundredths. Next one goes out to the thousandths. Which one's the least precise? Hundredths, which means our answer needs to be reported to the hundredths. This is kind of interesting. How many sig figs in our numbers? 5 in our answer. How many sig figs did we start with? 3. Wait, what? We got more sig figs than we started with. Can we do that? Addition, subtraction, we can. And in fact, we will often find that we will lose significant digits as well. So we will set up experiments in such a way that when we look at differences, because that's where we typically lose sig figs, we're going to look at a difference between two numbers, that we make sure that difference is really big. Because if it's really big, we have more numbers, so that when we do the subtraction, we don't lose as many sig figs. Okay, we can keep as many as possible. All right? So it is fine to increase sig figs. There's one other issue with the number as written, and this one is not in the answers. This answer boxed in red is still wrong. Label, that's a nice way to say it. We're going to do label. We need the units. It's meters. Okay. Next one. You guys already all saw the answers written down there. 4540. That's missing some stuff, isn't it? Okay. Is this our appropriate number? Okay, what did the calculator spit out? I should have written down what the calculator spit out. 4538 point. What was the next sequence?
47.
47, that's close enough. So your calculator gives you all these numbers. That number is going to come out wrong. Or that answer is wrong. Because we go back, since we're doing multiplication, we go to the fewest number of sig figs, which is 3, which means I can only carry those 3 sig figs. So I look at my first insignificant digit, that 8, which is bigger than 5, which means I have to add 1, and my number becomes 4540. Why do I keep doing that? 4540. Units become meters times meters times meters, which is meters cubed. Interesting question. Is this number correct? I'm not adding a 0 there. There's a decimal point. Actually, I think I see what you're talking about. I'll come back to you in a second. Okay, okay, we won't come back to that. We'll start with that right now. So, what is this number right here? Someone read that number off to me. 4,538 point whatever. Okay. If we just write with our proper sig figs 454, read that number off. 454. Is there a difference between 4,000 and 400?
Yeah.
That's a pretty significant difference, particularly if that was a paycheck. Okay. We need that 0. That 0 is our placeholder to tell us that that 4 is in the thousand place. It is not a significant digit, okay, because there's no decimal point, which now gets to the question that I was going to ask. Is this number now correct?
No.
No, because now I have 4 sig figs, and 4 sig figs is incorrect. Okay? So we have to make sure that that decimal does not show up so that we maintain those 3 sig figs. Sweetness. Yes?
What if that 8 was a number that was less than 5?
I will admit what ifs are kind of dangerous. So let's look at a new number. Right, new calculation. I don't care about all the rest of that now. We wanted 4, 5, 3, 2. And I said I wanted this to 3 sig figs. What answer do I report? 4, 5, 3. This number is less than 5. So it disappears. The digit disappears. Right? And I don't add anything to that 3, and the number I come up with is 4, 5, 3 placeholder. Make sense? All right. We need to go through the rest of the answers? Okay, well, I'm going to erase everything just for the moment. Erase everything. The next answer is... no idea why the units say grams. But that's interesting. 0.03 liters. How many sig figs in that number? 1. How many sig figs did we start with? 4 is our fewest amount. We lost a lot of sig figs in this calculation. Is that allowed?
Yeah.
It's addition, subtraction. This is where we can lose sig figs, is with subtraction. We can only report out to our least precise measurement. The least precise measurement is right there, to our hundredths place, which means when we go to our answer, there's our hundredths place. We have to stay there. Okay? Last one, which I think will be interesting just because of the units. If we trust my calculations, we come up with 0.0, oh man, another 454. 454. We're doing division, so we go based off the fewest number, the fewest number of sig figs. So we've got 3 sig figs in that first number, so our answer gets reported to 3 sig figs. 454. Why do the zeros not count? They're not preceded by a significant digit. Where this number or this question becomes more interesting is with the units. What are the units? Grams per centimeter cubed. And as we will find, this nice little slash method that everybody is so fond of doing is a load of crap, and you should stop doing it. It's 454 grams in the numerator over 1 centimeter cubed. Very subtle difference. Makes a massive difference in your calculations. Split it into the numerator and denominator. I know we hate fractions, deal with it. Get it into those fractions. Okay? Questions?
Would you not accept centimeter cubed because you're inferring that that is just 1 anyway?
I would accept just centimeters cubed underneath without the 1. Okay? The only reason I include the 1 is it gives me a number that I can play with, so that every place in my numerator or denominator I have a number and a unit. Okay? That number can't be anything other than 1, because if it's 0, 454 divided by 0 is not 454. And if it's any other number, I'm now doing a division. Okay? So the 1 is there just as kind of a placeholder number so that I know there is still a number there. Okay? You do not have to include it, it just helps you to see it. Whoops, I did that right. Wrong. I did that right. Good catch on that. It would be 0.0. I got something with the 454 issues, apparently. You're right. Your number was 0.0454 grams over 1 centimeter cubed. Thank you for catching that. Other questions? Okay. Some simplifications. Okay? since none of you printed out the notes, I can make you write this. Right, 4 times 4 times 4 times 4 times 4 times 4. I was kind of kidding. You'll notice that as you go through and write that out, that gets kind of tiresome, right? So what simplification do we come up with? Okay. We can deal with the powers. Okay, so we can do 4 to the power of 6. Okay. The bigger issue is going to be entering this into our calculators. Okay, so if you go through and do 4 times 4 times 4 times 4 into the calculator, it's not that big of a deal. It's a lot easier than just writing it out. Okay, entering 4 to the 6th into the calculator should be a little bit easier, but you will notice that with this power comes great responsibility. It just came to me. It is very easy to make mistakes when entering into the calculator with these powers. Okay, so if at any point you're having problems getting the correct answer, either by doing the back of the textbook or back of the chapter problems and not getting the answers the back of the book is giving you, or going through mastering and not getting the answer the mastering is giving you, it is very likely a notational issue that you've run into with the calculator. Right? I'm not going to spend any time on entering that into or discussing that in greater detail in class, but if you do have problems manipulating your calculator, you need to talk to me, because that is not something you want to find out when you start the exam. Make sense? We can also go through and do it with units, which we already did with the meters. We ended up with meters cubed. So m times m times m, we can't simplify to a new number, but we can just say it's m to the 3rd power. Okay, so we can come up with these nice little exponents. The other thing we're going to jump into is powers of 10. Come on, by the power. Typically used to simplify our insignificant digits. Some people got that reference, apparently not so many others. So where we were talking about with that, and this is kind of a nice case to pull it up, is if we looked back at that number where we had 4540, NPR said, why keep writing that 0? Well, that 0 was important because that made the 4 in the 1,000 place. It made that 4,000, not 400. Okay? But now I put that 0 in there, and we start to get nervous. Am I counting that as a sig fig or not? It kind of makes me nervous. So what we can do is convert this number into scientific notation. So we can take our implied decimal place and shift this over and come up with the number 4.54. Now I'm not going to show the 0, because if I include the 0 now, it becomes significant. And I can say multiply by 10 to the power of 3. Okay? So I can now remove some of that ambiguous 0 sign or sig fig issue by converting it into scientific notation. Okay, so we get all these powers of 10. You can go bigger, you can go smaller, depending on what you're trying to do. Yeah.
Chemistry accept that?
It should. The issue, 3 different homework systems, so I got to track it down. I think the issue with mastering is it does not accept 4.4x 10 to the 3rd. But it will accept 4.4 times 10 to the 3rd. So if you use their x in their little multiplication thing, it's okay. And somebody, different class, showed me there's some kind of hot button key that you can get a little dot showing up. The dot is the same thing as the multiplication. I don't know how to get the dot. I'm not sure if it's the asterisk. It is the star, so it is the asterisk, which is shift 8. Yeah. Shift 8 will give you your multiplication too. But x does not work. It interprets that as a letter, not as a mathematical symbol. Okay? Regardless, within your settings, mastering should accept, say for this calculation, if you wanted to come up with it, I don't remember what it was, grams. Let's just say it was grams. It should accept both of those as valid answers. It doesn't, let me know. I'll have to take a look at it, send them an email. I'll probably delete the question or give you extra points. This is also one of the reasons with these notational things, you got the answer right, but because of some weird grading issue, mastering took points away. This is one of the reasons why if you get 90% or above on mastering, you get 100% of the points. Okay, so I do kind of account for these kind of nuances within it.
So if you get 102, does it?
You get 100. You can talk to me more about that if you want. So if we want to represent a really small number, What do we do with our power of 10?
What did I do?
We just make it a 10 to the negative power. And now we shift to a very small number. Okay? So we're just playing around with those to help us shift different places. 55.
Yeah.
I got to remember this time. Next thing we can go through and do is deal with scientific notation, which is ultimately dealing with our powers of 10. It's kind of it is ultimately just lazy. You don't want to draw in all those placeholder zeros. So we come up with scientific notation so we can ignore those placeholder zeros by dropping it into a powers of 10 situation.
So mathematicians are just lazy.
Well, you could call it mathematicians, chemists, scientists. Okay, all of us are lazy. And you're really going to tell me you're not lazy? Yeah. Okay. In general, we are straight up lazy. We'll do whatever we can to shorten the amount of work that we've got to do. Okay. So we can use the scientific notation to deal with that. So if we were going to convert the distance between the Earth and the Moon, we can convert that number into what for scientific notation? So in our scientific notation, we only have a number in our ones place. No tens, no hundreds, no thousands, any of that. Only in the ones. We then string the rest of our numbers after the decimal, and they can only be our significant digits. Thankfully, I didn't include another number in there. We now do times our 10, and we want to see how far we shifted our decimal. So I go 1, 2, 3, 4, 5, 6, 7, 8. It's even more fun if you look at your calculator now. Look at the screen. It's probably nice and just kind of polished and neat. By the end of the semester, you will probably see a bunch of these little arrow things across the top of the screen. There is a shortcut to telling your calculator to spit it out in scientific notation. I can help you with that too. Okay. I already forgot. How many positions did I shift?
8.
8, 9? We'll say 8. 10 to the 8. Okay? And our unit meters. The other one, 1.16 times 10 to the, how far do we shift this one? 1, 2, 3, 4, 5, 6. Just trying to prove you wrong. To the 7, really?
-7.
It's got to be the -7 because we're looking at a number that's really small. Yes?
Why can't you have like 4,063 times 10 to the 4th? Why?
I see what you're saying. So why do we have to have it for scientific notation where the only number bigger than the decimal is the ones place? It's just the rule. Okay? Why is a dime worth 10 pennies? We said that's the way it is. Okay? You'll see numbers where you have 4,000 times 10 to the whatever power. It's not officially scientific notation. I actually thought of that same question when I looked at this material a little while ago, because when you think of scientific notation, I just think powers of 10. Okay? Officially, ones place. Rest of the numbers after the decimal. It's just the way it is. Yep. Yay, metric system. You will find that being locked in scientific notation is probably not what you want, because a lot of times you don't want it in scientific notation. So it's up to you to decide which method you want to do. So metric system. We talked about some of these earlier. We talked about kind of the ludicrousness of our individual measurements, that ultimately we just have to deal with it. Our standard metric system for distance or length, we've got meters. Our mass will be grams, and our volume liters, and time seconds.
What's DA mean?
Okay. I don't know.
Oh.
District attorney?
It's definitely me. I don't know why I put it there. And I thought I deleted it because I couldn't remember why I put it there. I used to be called DA because of Davis Allen, right? So, but I don't know. I really don't. So those are our standard units within these. Officially, the standard unit, according to the metric system, for mass is not grams, it's officially kilograms. Okay. The reason why I don't like using it as kilograms is the kili is a prefix that affects the unit of grams. Okay, so if we think of our base units, meter, gram, liter, second, okay, we can then adjust those units up in different directions. but the kilogram is the official measurement for mass. It's just not our base unit. Make sense-ish? So what if we want to go to a really big number or a really small number? Well, we can deal with powers of 10 off of these, but if I want to look at the distance between Atlanta and Denver, I could go through and look at the meters. Okay, well, a meter is roughly 3 feet. Okay, since we understand feet a little bit better, I'm going to end up with a lot of meters. Okay, or I could measure it in feet. I'm going to end up with a lot of feet. Is there another unit that I could switch to make that number a little bit more sensical? I could switch to kilometers. Or in the US, I could switch to miles. Okay, so we can use different units to mean different things. One of the things that's powerful about our metric system is that we can go through and convert all of our base units, meter, gram, liter, second, by powers of 10 with these Greek prefixes. So when we look at a kilogram is K followed by a gram. So what does K represent? 1,000. So what is a kilogram? 1,000 grams. Okay, so that information can come off of it. There's all sorts of fun little prefixes that we could throw at you. Okay? Officially, what should you do? Memorize them all, because you need to use them. Okay? That is a lot of more stuff to go through and memorize. More often than not, though, you probably won't see pico, nano. You probably won't even see deci all that often, or mega, giga, or tera. Why are mega, giga, and tera kind of out of the question? Those are way too huge to work with. Why are nano, pico, and even micro way too small? Okay, so some of those you'll see show up in questions. If you see them pop up in questions, you don't have to have it memorized. This table is in your book. I believe it's on page 30, if I remember correctly from last night. It is? Yeah, see, look at that. You got some kind of memory. Page 30 in your book, you've got it available to you. So when you go through and do the homework, you should have this in front of you when trying to deal with these conversions so that you can go through and do them quickly. Okay? Yes, there's a little rhyming scheme that some mathematician came up with some King George Henry had fathers and babies and children, chocolate milk. Okay? And pizzas, apparently. I really dislike that method of dealing with your powers of 10. Okay? I'm not going to stop you from using it. I'm just going to say straight off the bat, I think it is an awful, awful way to do these conversions, because what you've done is internalize the powers of 10 conversion, which on its own isn't bad. But I think I've already mentioned this. What's the problem with internalizing? You are now going deep inside the recesses of your brain, which is a horrible place to be. Okay? So if you can get it out of your brain and onto paper, that's a much better place. So if you've got it memorized, write it down, get it on paper so you can interpret it off the paper, and stop internalizing your conversions. Write those conversions out. Make sense? Okay, so how can we use these powers of 10 to change our units? Before we even do that, don't memorize them all. 3. You will use these 3 a lot. So even though you have the table available for you for the homework, you probably won't have it available for you when you get into the exam. Okay, so these 3, if you memorize them, will make your homework go faster. Okay, since you're not having them on the exam, they're also the 3 most common that you would see on an exam. Okay, so then you'll be set. So get those 3 memorized. All you really need is the symbol, so K, C, or M, and then the power of 10 associated with it. Okay, if you've got that set, you should be good to go. If you've already got them memorized, good job.
Can I confirm that K is not capitalized for kilogram or kilo anything?
K is not capitalized. Why is that odd? Because when we go to big numbers, what happens to the symbol? You notice that we typically shift to capital letters. Kilo is not capitalized. Don't shoot the messenger.
It's not big.
Okay? It's a lowercase k. It's the way it is. So we got some practice. Whoa, come back here. So here's where we got some practice. I want you to convert these numbers into scientific notation. Okay, and then I want you to give me the number and the new unit. Because I know you got these all memorized that quickly. So the new unit. So I don't want you to give me meters, seconds, liters, or grams. I want the new Greek prefix unit that's going to be associated with these. Okay, so based off of these powers of 10. If you got questions, so we've got our powers of 10, and that next one, we shift the decimal place 2 spots, smaller, -2. Our unit was seconds. We again can group our power of 10 with our seconds, and we get 1.2 centiseconds.
That sounds cool.
Next one, 1, 2, again, -2, sorry for the change in color. 1.2
Centiliters?
centiliters. Last one, 1, 2, 3, -3, already forgot the unit,
Milligrams.
grams. 10 to the 3 is milli, you get 1.2 milligrams. So we can drop in those kind of conversions kind of nicely based off of those powers of 10. So it's kind of fun.
Keep the L capitalized for liters.
Sorry, what was that?
Keep the L capitalized.
L is capitalized for liters. It is a capital. Other questions? None? Okay. Fractional notations. I'm not sure how much I really want to get too much into these next sequence of slides because it seems to confuse more people than help. But we need to look at some of our units and kind of come up with their understanding of these. So we got our symbols up here. So let's take a look at kilometers and meters. So we deal with that. Our English is there are 1,000 meters and 1 kilometer. English is cool. Everybody goes, okay, yeah, I understand that. Now we try and convert that into mathematics. Okay, well, we can say 1 kilometer equals 1 km. So we shorten the English down because we're lazy. Equals 1,000 meters. So that helps us out as well. We now have this into a mathematical expression. So here's a new question. Is this true? 2 equals 2. Okay. So what is 2 divided by 2? 1. Is that valid? Yeah. All I'm doing is shifting this now so that I'm doing pretty much, if I wanted to multiply them by something, I'm multiplying by 1. That's cool. I can do that mathematically. Okay. How about this option?
Why not?
Yeah. Okay. Instead of being 2 over 2, it's 2 over 2. Okay. We get the same answer. It's still 1. This notation, which is what we were getting at with that grams per milliliter or grams per liter that we had earlier on, right? Getting our units out of straight lines and into numerator-denominator. Okay? The numerator-denominator is really going to help us out when we deal with our calculations in units that we don't understand. Okay? Students tend to be very good with dealing with this section and think it's boring. Oh, why do I have to bother with this? I can do all this in my head. Yeah, you can, but what happens when I change the unit? You can't do it in your head. You have no frame of reference, and now you go, well, it's impossible. You're doing the exact same thing, okay, with units that you don't understand. You have to find a frame of reference for the conversion factors, and then you just have to kind of trust them. Okay, so this numerator-denominator thing is going to become incredibly important. Okay? I don't want to look at that one. Yeah, I also don't want to look at that one, so you probably want to ignore that. So let's just take a look at some other mathematical tests here. Okay. Last night they were just like, oh, this is easy, just move on. Let's pause for a moment, because I'm nicer to you. What happens? How can we solve that first one? The 3 can cancel with part of the 6, and we end up with 3, 6 over 2. Okay. So we can go through and simplify with our numbers. But if I go through and throw this in, now everybody goes, well, holy shit, what the hell did you just do?
2,000 combined meters.
What happens? Meters cancel, and I get 2 over 1,000 kilometers. You're used to dealing with math. The numbers you seem to cancel and deal with relatively well. But as soon as we bring in symbols or letters, everybody freaks out. It's the same thing. All right? So be kind of aware of that. We can go through and cancel these units the same way as we can cancel our numbers. Okay? So,
That's pretty.
I have a feeling that was the last slide.